Estimation the influence of non-monotonic loading regimes on the Portevin-Chatelier effect in the aluminum-magnesium alloy. Experimental study by using the DIC. This work is about the experimental study of the spatial time and homogeneity of plastic deformation in structural metals and alloys due to the Luders behavior, the Jackie flow or the Portevin-Chatelier effect, and the post-critical deformation and the strain localization. It is important to estimate the influence of the different mechanical parameters on the plastic flow of metals, such as temperature, loading rate, and loading conditions, the stiffness of the loading system, stress concentrators, and geometry of the specimen, and the additional vibration impact. And of course, it is important to develop the test procedure based on the combined use of several measurement systems, such as the DSC measurement system and the infrared camera. So this work is aimed at the experimental study of the effects of intermittent deformation of aluminum-magnesium alloys and the development of multi-level models of inelastic deformation under complex loading conditions. So this work is about the studying the temporal instabilities and spatial localization due to the Luders behavior and the Portevin-Chatelier effect. For this study, we have several stages or parts of investigation, such as influence of stress concentrators on the Luders behavior. The next part is the study the influence of additional cycle loading on patterns of the serrated flow. The next one is to estimate the influence of loading system stiffness on effects of spatial time and homogeneity due to the Jackie flow and strain bands propagation. And the last one is to study the influence of non-monotonic loading regimes on the POC effect. Some words about test procedure. So as you can see, the loading was carried out by the biaxial servo-hydraulic testing system Instron 8850, and we provided analysis of strain and displacement fields by the DIC measurement system Big3D. At first part, as I said, we studied the temporal instabilities and spatial localization due to the Luders behavior in simple conditions. We tested flat specimen during the uniaxial tension test with different loading rate. We analyze the evolution of the longitudinal strain fields at the first stage of uniaxial tension. We can see the series of profiles of this deformation, and which is plotted at equal time intervals along the length of thin walled of a flat specimen. During this test program, we had the main result that increase of the loading rate causes the proportional increase of the velocity of the strain bands propagation. Also, we have estimated several parameters which characterizes the Luders behavior. You can see the coefficient of the homogeneity of the plastic flow. Next one is the velocity of the propagation of the single strain band and several others. Also, we studied the spatial time inhomogeneity due to the POC effect, and we analyzed continuous propagation of a single band by the POC, due to the POC effect, and the stochastic nucleation of bands, as you can see on the strain fields. And to analyze the process of inelastic deformation in such materials, we draw the profiles of the longitudinal strain along the surface, and you can see that there are several stages when one strain band is when one band started and propagate along the specimen, and also we can see this on the temperature fields as well. So we can see the quasi-periodic character of the development of plastic flow, and it is interesting to analyze this character, this behavior in different loading conditions. So the next part of this work, we studied the influence of additional cycle loading on patterns of the circuit flow. So as you can see, we had some results about loading, about additional vibration impact on kinetics of strain bands. If we look at the loading diagrams obtained for this specimen without and with additional vibration, we see that the behavior is similar, but the nucleation of strain bands is a little bit different. And if we saw through the set of profiles as at the previous stage, we can see that the character of the behavior is different when we have the additional vibration impact. The quasi-periodic character is not so stable, and the propagation of POC bands is not so stable. Next one, we studied the influence of non-monotonic loading regimes on the POC effect. So we took the thin-walled tubular specimen for tension-torsion tests with different components. So we wanted to realize the spatial velocity of of the deformation of materials. So the calculation of the intensity of deformations is made according to the following equation. And for the case when only a tension load and or torque act on thin-walled tubular specimen, the intensity of deformations can be written in the following form. So in the table 2, you can see different values of velocities by deformation components for various types of tests. So in this series of tests, we used extensometer to control the loading rate, but the test methodology, due to its limited range of strain measurement, we need to make several stops to reinstall the extensometer. So you can see that on the diagram we have at first part we have at point 1 it's a stop on the elongation of 3.5 millimeters and unloading and reloading, and you can see that this stop propagated the POC effect, and we decided to provide this test without unloading and reloading. And the next one test we provided without unloading. So the stop for reinstallation of the extensometer was implemented at a lower value of the achieved elongation, but even at this level of deformations, after stopping with further proportional loading, a process of inhomogeneous intermittent deformation is provoked. So at point 2, the extensometer was also reset when the loading process was stopped without unloading. So experimental data show that stops, even at small values of plastic deformations, further loading leads to the occurrence of inhomogeneous intermittent plastic deformation process. This is reflected in the recorded deformation diagrams in the form of the POC effect. So when we decrease the elongation level, or when we stop the loading and then we continue our test, on the diagram we can see when as the POC effect starts and the level is lower than at the next stage, on the previous stage, sorry. Then at the last part we decided not to use the biaxial extensometer, but we calculate the velocities for tests by and we will control by the built-in sensors of the test system. So we have these curves, and of course it is interesting to analyze the POC effect under proportional loading. As you can see, the series of plot of longitudinal deformations, it is interesting to see the moment when the POC effect starts, and for example we showed the process of initiation, the first POC bend and its propagation along the points 1 to 5. It is interesting to analyze the behavior of the POC effect not only during uniaxial tension tests, but also in tests with complicated loading conditions, and we will continue these investigations in that way. So this work was carried out in the Center of Experimental Mechanics in the Perm National Research Polytechnic University in Russia. So thank you for your attention, and we are open for collaboration. Bye bye.